everyone. Thank you for tuning in. If you've been here before, welcome back. And if you're here for the first time, thank you for joining. Today, we're going to have a session on the practice of doing performance analysis and optimization with TensorRT-LLM. We're joined by two awesome speakers. First up will be Caillou, a compute architect engineer who's actively contributing to TensorRT-LLM and focusing on general performance. And then we'll hear from Cyrus, an AI developer technology engineer who's actively working on LLM inference framework kernel performance analysis and optimization. Caillou, take it away.
Thank you. Hi, everyone. So today I'm talk about, me and Cyrus, we are going to talk about the practice of doing performance analysis and optimization with TensorRT-LLM. And we have agenda that have 5 parts. So I'm going to take the first 3 parts that includes the use some of the useful tools and tips for performance analysis and do some actual practice on optimizing that on the system level. And Cyrus is gonna introduce on how usual CUDA kernel analysis is being done and how optimization is gonna done in the TensorRT. So I think today I'm not gonna introduce too many details on how those optimization is being landed into TLDR, but more focused on, we're gonna focus more on the how we are gonna use those tools and how are those tools and the functionalities that are provided by TensorRT going to help with the performance analysis. So let's get started. So first of all, I want to share the mostly used example command that we used for debugging and for benchmark TensorRT in a very typical scenario. And so this is a command when you are trying to use TLDR bench to benchmark TensorRT, and when you are trying to use assist profile to profile the timeline that how TLDR bench is doing the benchmark. And you could also you could certainly replace the TLDR bench command with the TLDR serve command. But the assist profile idea is the same. So it basically uses several different chases. It uses CUDA profiler API, and it enables some of the environment variables provided by TensorRT to get more information and to have a better way of debugging and find out more information on how TensorRT is implemented and how it will functionally work. So you could also refer to the document that I put in the link, but I'll go through some of the most important environment variables and arguments that are involved in this command. So the first 3 helpful environment variable includes TLM profile start stop, TLM NVTX debug, and TLM profile record GC. So the first one, the TLM profile start stop, will help you to only correct specific inference iterations. For example, from A to B, like from 1 to 100 or from 100 to 200. So what's that gonna do is that will help you to narrow down the focused performance hotspot. For example, if you if you just want to see how the program is running when GPU step is between 100 and 200, or if you are end-to-end, for example, if your end-to-end program is running like for 1 hour or 2 hours, and you cannot actually just profile the entire 1 hour process of the benchmark, then you can use this way to reduce the profile size and to only focus on the part that you are interested. So you could use this environment variable, and TLTM will only profile the specific range of the iterations, and it only take effect when you also append -c CUDA provider API, which enables the programming way of NSys profile command, and that and the corrected timeline will just be narrowed down to a-b. And the second environment variable is TLM NVTX debug, and that one actually just enable more NVTX markers for better debugging, because we have prepared many NVTX markers in the system on different locations, and if you enable this environment variable, those markers will be visible. And also it include we've added a environment variable called TLM profile record GC. So if you set that 1 to 1, that means you can enable the Python GC NVTS markers for the users who want to get hints when the time is actually spent on GC. And there's a snapshot that the diagram is actually showing how the Python GC markers are gonna show on the timeline. In this case, it takes almost 4 milliseconds. And this way you can actually know when it's waiting, when the Python GC is actually taking the taking the CPU work. So moving further, there's one more very helpful, and I actually use it a lot, profile option, but this one is actually implemented by NSys profile, and it's called Python Geo. So this one enables Python global interpreter lock, aka the Geo markers, together with the other informations when you are using commands like NSys profile. And I usually enable it together with CUDA and VTX, and you could also refer to the official documentation of NSys profile to see more information. And this argument is also very helpful and being heavily used when I'm debugging the performance of TensorRT when it happens. I mean, when you want to take a look at the performance status of the system. So especially when you are analyzing the Python behavior on CPU, because it actually tells you how Python is occupying the resources by acquiring the geo. And because sometimes if you see that a specific NVTS marker is very long, you might be confused that why it took so long, and sometimes it in fact does not take such long time to just for CPU to finish the operation, but most of the time is that CPU is actually waiting for geo for on the other thread. And I also put an example here, and this one is a very typical example when one thread is waiting for another thread to release the geo. And you could see that the on the green bar, that the darker green bar is with the text holding geo on it, is the one that the corresponding thread is actually holding the geo, while the other thread on that process are waiting for that specific thread to release the geo. And that's basically what how Python Geo is working in Python. So this is very helpful because TensorRT, the most part of TensorRT, including the LLM API and the core library, is implemented on Python. And Python has this specific geo mechanism, we need such functionality to decide where actually the hotspot is. So based on some of this brief introduction on how those tools are used and how we can profile and do some performance analysis on it. Um, we can moving we can moving one step forward and um, take a look at overall implementation, and then I'm gonna introduce two specific examples on how we use those tools to analyze the performance and try optimize it. So the overall implementation of current TRT-LLM on system level is that we I mean this is a simplified model, but it explains how it basically works. So we have mostly two processes. The main process is going to be the process that handles the server and handles the user interface. So it receives the request from the user, and it also will be responsible for spawning an MPI process, and then we're going to have a worker process. So those two processes are the major processes that are handling the most of the Python implementation in TLTRM. And when the request is reaching the main process, it will be firstly just directly given to the worker process through inter-process communication, and also the main process is going to spawn create different threads, and the worker process are going to create different threads as well. And so the worker process will create one important thread called await response thread, and then when the request is passed to the PyXCUDA, the PyXCUDA will launch the specific XCUDA of the the actual implementation of the XCUDA, such as PyXCUDA or CPP runtime XCUDA. And if the request is given to the PyXCUDA, it will launch kernels, and it will finish the calculation needed. And for example, for LLMs, output IDs are going to be generated, and responses are going to be generated by TensorRT-LLM. And when responses are generated, the first thing is that we're gonna pass the generated responses to the await response helper, and that process is a communication within the process. And the thing that await response worker or helper is trying to do is that it will forward the responses back to the main process. So you could see that there's one more inter-process communication, and the await response helper will give the responses to dispatch result task. And the dispatch result task is another thread that is created by the main thread, and it will be responsible for giving those responses back to the detokenizer. And under the case when user is enabling the detokenizer, it will give the responses to the detokenizer, and the detokenizer is gonna do its work and converting the token IDs to string, and it will and afterwards the main process will also create the final responses. Like for example, for TLTM serve, it will give the responses back to the OpenAI API server, which is built based on the fast API server in TensorRT-LLM, and all those responses will go back to the user in the as the last stop of its life cycle. So this is the overall implementation, and if you are trying to profile TensorRT-LLM, you are going to see something interesting because the profile or the timeline you're gonna see is that it will be very similar or it will reflect how it worked as I just mentioned, and you could see some interesting details based on that. And this is a very so this is an example of what you will see when you are trying to benchmark and profile TLDRM using the command I mentioned earlier. And this one is an overview back to the version of 0.20.0 RC1 because I use that version to demonstrate what it was like before we landing in some optimization. And and by the way, you can find the latest version and on GitHub, and we are currently um, preparing 1.0. And we have published some release candidate version. And when you are benchmark and providing the implementation on the latest version, you could expect something different than this one I just mentioned. And so back to the timeline, you could see that there are several different processes and threads, and we could roughly mirroring the processes and threads back to the previous page. And we have CUDA, we have a wait response helper, we have the dispatch result task and the detonizer. And this only reflect the second part of the life cycle of a response because I skipped part when the response gets created. So you could see that there I marked several annotation or the red boxes there on the graph, and it means it is trying to explain what's happening to that responses at that time. And for example, when the responses are created on the PySQL, it's going to be serialized and deserialized when we are doing a roundup or gather for features like attention DP, and then it goes to await response helper, which is in-char process communication, and the await response helper will send all those responses to another process, which is an inter-process communication, and which introduce a a set of serialization and deserialization, and also of course a send. And when the dispatch result task receive the responses, it's going to forward that one to the detonizer, and the detonizer is going to I annotated as prepare outputs, but it's actually doing something like detokenizing the tokens and prepare output OpenAI server output for the final for the endpoint users. So we could actually see the implementation idea of TensorRT by just profiling and benchmark and profiling the models, and we could actually observe the way that how it's done by inspecting the timeline. And also so if we take a look at this graph, we could see that there are several parts that looks confusing. And for example, if we take a look at this part specifically, you could see that those responses
Actually,
are.
Caillou, I think we've got a couple of questions. Let's take a moment real quick before we go to the next slide to answer one of them. and I
Sure.
will bring it up on screen for you.
Let me see. Yeah, that's a very good question. And I think currently in internal of NVIDIA we are using several different Slurm clusters, and that part was actually taken care by the Slurm clusters, and the Slurm clusters is going to be responsible for things like doing the actual spawn. And also together with the MPI library, they are going to be responsible for the actual implementation of the spawn and the process affinity um and we rely on the infrastructure to guarantee the performance of like something like inter-process communication, um, and 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 that's also the same for multi GPU for multi GPU communication, and also between multi nodes communication. That should be the same.
Thank you.
Okay, I'll move on if that just the question, and feel free to let us know if I'm not being clear. Um so um as I was discussing, this one here is all those responses have been experienced different stages of serialization, deserialization, and then serialize again, and then deserialize again. And there's one um, set of duplicated deserialize and serialize. And so we were seeing the same issues there, and we were thinking about how can we like remove the duplicated serialization and deserialization. Um, and we did some analysis, and we optimized the second part of the deserialization and serialization by delaying the the second deserialization to a later stage. That helps on two aspects. One is on one is that um, it saves some time, which will benefit TDFT. And the second advantage is that it will also reduce the size when we are doing the inter-process communication, and that will make the communication like the MPI altogether, MPI um, um, broadcast faster. So that one is one of the optimization we landed in when we are seeing this profile results. And another example is very usual is a very usual case. So some of the cases especially for streaming mode, we usually make the assumption that each iteration has to return responses for every request that includes the token generated on that iteration. So for example, when streaming is enabled and when the output length of the specific prompt is 10, then 10 token will be generated, and on each GPU step or each GPU iteration, one token is going to be returned. I mean, one response is going to be returned for every single token, single token. So um, so when the batch size is very large, that will actually lead to a very heavy CPU operation and for the CPU work, and that could take a lot of time. And we have observed actually some extreme cases when we are supporting the scenarios when the batch size is very large, and that is when CPU cannot even finish all those operations before the next GPU iteration starts, and that could significantly affect the streaming performance and the final throughput. And this corresponds to this part on the diagram I shared earlier. So in order to resolve that, we introduced a stream interval feature, and so the logic of that feature is that instead of handling all responses on each iteration, we allow users to specify a argument called stream interval, and you can set it to n, and that n will means that the responses will be handled and returned every n iterations. That way, on each iteration, the output ID itself will still be generated by GPU and being calculated by GPU, but it won't be returned to users immediately, except for the first token for TTFD. However, the tokens will be accumulated for any iterations, and one and afterwards one response is created to handle those and generated tokens. And this actually helps reduce the pressure on the CPU side, and it gives more chances and more time for the CPU to catch up the work that GPU is doing, because the CPU has to be faster than GPU, otherwise GPU will be waiting for a CPU, and that will lead to bubble on the CUDA stream. So so in order to see the effect of our optimization, this is an I put a diagram here after the optimization, and when the user, on this case it should be 16, and when a user is specifying a specific stream interval, all those responses handling work like tokenization, detokenization, and preparing OpenAI's API server outputs are going to be separated to be limited to specific iterations, and it will just give the CPU more time to catch up. And this one is useful for streaming performance, and it is also very recommended, and also the impact, the influence can be clearly observed on NSYS profile when you are profiling the program. And yeah, I think that's all for my part. And yeah.
All right. Thank you, Caillou. Before we move on to Cyrus's part, let's answer a couple more questions. So we have a question on multi-GPU profiling.
How do your profiling and optimization change when scaling from a single chip, especially regarding collaborative kernel fusion cross devices? Yeah, that's a very good question as well. And for this one, it actually, so let me just quickly go to the previous page. So so this command actually, it won't change too much, but the case that you want to be careful is that since this is this command is only for one process, so if you are going to for example, if you are going to profile a multi-GPU program using this command, you may want to separate different profile file names, and so that it won't try to write the profile, the timeline profile to the same file, which will lead to conflict. Other than that, I think all those commands can all those arguments can be just reused, and they are common between single GPU, multi-GPU, and multi-nodes.
All right, and then one more question for you.
Which did you? Yeah. As a very quick kind of like the verification, we can just use TDFT and ITL, that is time to the first token and inter-token latency, and also the overall output throughput, output token throughput, and that those metrics will be used to measure most of the performance improvements we are doing, because most clients will clients will care is DDFT, ITL, and final throughput, and we use those specific metrics for those performance optimization, including the deserialized serialized optimization.
All right, great. Looks like those are all the questions we have for now. Let's move on to hearing from Cyrus.
Thanks, Harry, for sharing the runtime performance analysis and optimizations. So I will share the CUDA kernel performance analysis and optimization with the several like real cases we have been doing the kernel optimizations in the TensorRT-LLM. So the first step to analyze the CUDA kernels is to use the NSAT system, the NSYS, to locate the slow kernels. So in the NSYS, here we use the DeepSeek R1 IP8 block scale quant kernel on H200, which was on the version 0.19, where we found this like in the NSYS there is like if you expand the total kernel times, you can there is a mapping of like each kernel's the percentage of each kernel's took. So in this example, we can see this like scale 1 multiply 128 kernel, which is the IP8 quantization kernel took about like 12.8 in the total time. And also in the timeline, we could see like this there are sometimes to be very long, like this kernel before the matrix multiplications, which is very strange because the quant kernel is the element-wise kernel, which should be very small and quick. So in this case, we know like where this kernel might need to be optimized. Then after locating the slow kernels, we need the more details and more detailed information and the analysis of these kernels. So we need to use another tool, which is the NVIDIA NSAT Compute, the NCU, to analyze the kernel performances. So NCU is an interactive CUDA kernel profiler that provides detailed performance metrics and API debugging for the CUDA applications and the kernels. So the best practice using the NCU to profile a kernel is first to isolate out the kernel from the TensorRT-LLM and then use the NCU to generate the profiler report for that. So when we open the NCU report, there will be we will see several kernels with its name and its duration. So here we have like 6 kernels, and they are actually all the same kernel, but with 2 different problem sizes. So it means like each kernels have 3 identical profiles. To see the details of the profile, we can just double click one kernel, and it will lead us to the details tab. So in the details tab on the top right, in the view section, in the view button, click the expand sections, and it will show all the details of the kernel performances. So there are several very helpful sections and when analyzing the kernel performances. At the top of the details tab is the GPU throughput table, which shows the compute and the memory throughput. So with this data, we could identify whether this kernel is memory bound, compute bound, or latency bound. So in this example, we could see both the compute and the memory throughput are very low, which indicates it is a latency bound kernel. Latency bound kernel usually happens when the kernel is small, which can confirm our assumptions in the NCU. So the next helpful table we usually use is the warp scheduler statistics table. So the first line is the GPU max warp per scheduler, which is 16, because in the GPU design, one streaming multiprocessor, one SM, has 4 warp scheduler, and one SM has at most 2048 threads. And one warp has 32 threads. Therefore, one warp scheduler has at most 16 warps. And the on the second row is the theoretical like warps per scheduler, which means like how in theory how many active warps can be in one scheduler of this kernel. So in this case, it is 16 means it can reach the max warp per scheduler. So the third line shows the real active warps per scheduler, which is in our case is only 1.99. So compared with the 16 theoretical value, it shows like the SM is very underutilized. So the parallelism of this kernel is not very enough. The next useful table is the warp stall chart. So the stall in GPU usually means like the warp stops and the wait for some processes to finish before they can continue to work. There are multiple reasons of the causes to the stall, and the NCUs can help to list all kinds of like stalls and analyze their performances. In this example, we could see the most significant stall is the stall long scoreboard. Stall long scoreboard means like the warp is stalled waiting for global or local memory read and write. So to be more specific, there are some operations inside the kernel which is waiting for the memory read from the global memory in this case, which makes the GPU not efficient. So the next table is the occupancy table. Occupancy is the ratio of the number of active warps per SM to the maximum number of possible active warps. So usually higher occupancies doesn't always result in the higher performances. However, low occupancy always reduce the ability to hide latencies, resulting in the overall performance degradation. So we could see like in the table, the occupancy of this kernel is only 12.39% compared with the theoretical 100% occupancy. So this indicates the SM is very underutilized, which is like which synced with the previous slides, the warp scheduling statistic table. And on the right side is the block limit calculator, which is used to calculate the block limit per SM to reach the max occupancy. So we will cover this part later in the slides. And there's also another type another type in the NCU report, which is the source type. So NCU can help correlate assembly the SAS codes with high-level codes such as the CUDA C codes. In addition, it displays the instruction correlated matrix to help pinpoint the performance problems in the code. So in this example, we can see it highlights the code that causes the long scoreboard with this like yellow triangle sign. On the right is like this part of code is calling the 99% of the long scoreboard. And going back to the kernel, to the left it shows which kernel is having this problem. So we could see like the problem line depends on its previous line's data, the input flag. The input flag is actually read it from the global memory of the input line. So regarding reading from global memory is a long latency operations in GPU. So the warp needs to wait till the read ends. This is the reason why the long scoreboard happens. And we can also notice that there is a for loop with like 4 iterations. So it means like each iteration shows this stuff happens in each iterations. So these are all the helpful tools we helpful matrix and tables we use while reading the NCU reports. And next I will discuss about how do we optimize this kernel based on the analysis on the NCU reports. So the first thing is to reduce the stall long scoreboard. So the left graph shows like the logics of the original code workflow. So each computation depends on its previous global memory read, and all the operations are done in serial. Done in serial. So to reduce the long scoreboard stall, we could split the global memory read and the computation to two different loops. So it can achieve better memory reads, and also it can overlap the reads and the computation to make it a pipeline instead of serial operation. In the meantime, we can use the vectorize the read to accelerate the reading from the global memory. For example, in this case, the input data type is 16-bit, either BF16 or FP16. So we could use the already provided CUDA 16-bit vector, which is the FP16.2 or BF16.2 vector, to transfer the uh, to to transfer the 16-bit read to the 32-bit read. It means like when reading, we're actually reading two 16 bits and combine them to be a 32-bit read. So it can save the instructions because the LGD 16 read instruction will be converted to the LGD 32 read instruction. So LDG is actually a SAS command, meaning like reading from global memory. So we are saving the instructions, and as well as we are uh, uh, our read will be more coalesced. So after the change, the new code will be look like this. And the second optimization will be how to increase the occupancy. So in the occupancy table, the NCU provides the maximum number of the thread blocks that can be resident on one SM based on different limits. For example, we can see the limited by the registers number, the shared memory size, the warp number. So in other words, the minimum value of all these values is the maximum value one SM should have to reach the max occupancy. So in this example, this value is 8, and in the original uh, in the original code when launching the kernel, we are only launching the number of SMs, which is 138 and 132 thread blocks. Uh, but from this table, we know we should have like 8 multiplied number of SMs, which is 1056 thread blocks. So with this simple change, we can see that now the occupancy has increased from like 12.39% to the 73.2%, which means like we're getting actually 5 times more or 6 times more occupancies. So, assigning more blocks to per SMs could assign like more warps to the scheduler, so the schedulers can see more idle warps when they are scheduling, so it can fully utilize the GPUs. So after the optimizations, let's see the result of the optimization. So compared with the original kernel, we could see the optimized kernel can have 6x more occupancy, 5x less kernel latency, 4x more compute throughput, as we can see in the blue and green chart, 2.5x less long scoreboard. So projecting this kernel speed ups to back to the end-to-end NCIS reports, we could see like the new this new optimized kernel now only takes 3.4% in the total kernel times, which means like we are reaching around 9% end-to-end speed up. Yeah, there's another kernel optimization which is really the kernel fusion. So which means like fuse several kernels into one kernel. Here we will use the fused gated MLP as an example. Gated MLP layer is a very common layer in the large language models, which happens after the attention layers. So the workflow of the original gated MLP is the input X will be sent to two different matrix multiplications, the fully connected FC and the gated up projection, gate up. The result of the FC kernel will be sent to the CUDA activation, and the result of the activation will have the inner product with the gated up result of the gated up projection. And then the result will go to one more layers, which is another matrix multiplication, which is the down projection jam. So from this workflow, we could see like the FC and the gated up jams actually are independent. They are two independent jams, and they use the same inputs. So it is like so it is very helpful if we can concatenate the input and wait well to merge to fuse these two jams into one large jam. So after we do this, the new workflow will be shown as at the right, which is like the input X will be passed into this the new fused gated up jam, which the input X will be duplicated, and the weight of the FC and the gate up will be concatenated. And after this gated up projection jam, they will go to the new activation kernel, which is the 3-GLUE kernel. So the workflow of this 3-GLUE kernel is like the input X will be split according to the last dimension to convert them back to the FC and the gated up kernel. So the FC will be passed to the CUDA as the original like gate up original gate MLP loops, and the result of the CUDA and the gate will do the inner productions, and this is the same, and the result will go to the down projection. So so what is the benefits of doing this kind of fusions? The first is like the memory bandwidth optimizations. So we could see in the original implementations, it needs two separate read and write from the global memories because usually the input is very large tensor. So they will be the read will be passed to FC and gated up. But now we only have one read and write because the weights are concatenated and we are just duplicating the inputs. The second benefit is the kernel launch time overhead reduction. So launching a kernel in GPU is not free. It needs some CPU. It needs the CPU to send the launching commands. So usually it took about 2 microseconds to 10 microseconds to launch a GPU kernel. So fuse the kernels into one kernel can help reduce the launching commands, which can help reduce some of the overheads of the causes by the kernel launching. The third is the better compute efficiency. So the one large gem is faster than two small gems because it has higher. First, it has higher arithmetic intensity, which means it has more flops per batch. Second, it also on modern GPUs, for example, Ampere, Hopper, and the new Blackwell, it can have better utilizations on the tensor cores because because the problem shapes are larger. The third point is like it could have better memory coalescing patterns, which means like reading one large gem, the reading efficiency will be much better than two different small gems. So as a result, we could see in the NC's report, the previous original implementation is around 89 microseconds, And with this new optimization, the new time is the large gem now is like 68 microseconds. So we are saving 20 microseconds, which is around like 20% more speed up on this fusion. And this fused-gated MLP now is these screenshots on the NCs are based on the old TensorRT backend on the H100 GPU. Now we have the TensorRT-LLM has the new PyTorch backend path, which we already applied this fused-gated MLP fusion by default. Yeah, that's my sharings today. Yeah.
Thank you so much. So at this time, if there's any more questions, please drop them in the chat. And then I've seen a couple of people ask about this. We're going to be adding a link to the slides in both the LinkedIn YouTube description, so you'll be able to find that afterwards. It looks like we have a question. How do you decide when to apply or skip fusion?
Yeah, this is a very good question. So usually when we want to do the fusion, we usually do fusions on the small kernels because first they are small, which means we usually do a kernel fusions based on the kernels. Like first it is like independent kernels on each GPU. So means it is not a multi-GPU kernel. For example, the all reduced kernel or gather kernel. Second, the kernel they are consecutive. This is the small kernel, so it can be fused to the larger kernels, or it can or there are several small kernels together, so we can fuse them together. The main benefits of doing these fusions is like reduce the global memory read and write and reduce the kernel launch overheads. Yeah, that's when we usually do the kernel fusion. It's like when we say consecutive small kernels, we do the fusion. Yeah.
Thank you. It looks like that might be all the questions that we've gotten. Okay, well, if that's all the questions we've had, thank you everyone for joining us, and we will see you next time.
Thank you.
Thank you.